Hey guys, I realize I haven't made a video in a really long time, and I've actually run into quite a few of you guys out in the wild saying stuff like, "Hey man, where you been? I used to love your videos. What happened to you?" And so the point of this video is twofold. One, I'm going to talk to you guys a little bit about what's happened to me over the past couple of years and where I've been, what I've been doing. And I also want to tell you a little bit about a project that I've been working on in my free time for the past however long. I knocked over a bottle. So, what happened to me is in 2016, which is I think when my video production ran off the cliff and I just got involved with other things. I think it was 2016. What happened to me was I got involved in a 3D printing startup with some friends of mine. We were designing our own 3D printer, we were sourcing the parts, we had some stuff custom made for us, like the frame of our 3D printer was an L-shaped bent aluminum thing, and had a square cut out so the gantry could go through. And we just got all these parts together. We were self-funded. We actually spent a fair amount of money getting this put together. We built our prototype. We got it working. It was at first it wasn't as nice as we wanted it to be because the frame wasn't as rigid as we had hoped it would be. We had to put in some struts to make that rock solid, but we got it working. And we think we had like a pretty decent 3D printer that like would work very well. We thought we had something pretty decent, but we couldn't really get funding. No one was interested in investing in us, and no one was interested in giving us a grant. Like we applied several places for it. It just didn't work out. And so when our own funding ran out, we just had to go do other stuff. And so what I did after that was, well, if you look at my channel's history, you can see when I designed and built Little Orphan Android. If you don't know what that is, it's a little Transformers animated wheelie toy that I designed and 3D printed through Shapeways. I've done actually a fair amount of that stuff since then. I don't think I've shown it to you guys, but point is, with that stuff and then the 3D printer, I actually have a pretty sizable mechanical design portfolio at this point. And so I took that to some friends of mine who run a research and development lab, and I said, "Hey, you guys got a job for me?" He said, "Yeah, sure, come work for us." And so I worked for them for a fair amount of time, and I left that job because my 3D printing friend said, "Hey, look at all this Bitcoin stuff it's doing. It's like $10,000 per Bitcoin. We're making our own cryptocurrency. That's super exciting. We actually got funding. Come work for us." And so I quit my job at the R&D factory and then started working on this. And we actually did a lot of really cool stuff. Like one thing we did was we built a decentralized exchange that ran on our blockchain. And the reason why, well, we sort of wanted to do this anyway, but the reason why we had to do this is because we had plans for running our own exchange, but we didn't want to have to deal with the Know Your Customer regulations that the FEC, I think it was the FEC, Federal Exchange Commission. Yeah, I think it's the FEC. The FEC put in place on crypto exchanges after the Bitcoin boom. And the reason I did that is like, well, clearly there's probably a lot of fraud going on here. We want to make sure the government gets its cut. And that just killed the Bitcoin bubble. But we still wanted our own exchange. And so because we couldn't do our own without having to go through all this bureaucratic red tape with FEC, we said, so really the regulation is about if we are matching trades for people, that's when you have to do the know your own customer stuff. That's what we figured. Don't take my advice on this, I'm not a lawyer, but that's what we figured. And then we said, so what if we make a decentralized exchange where people are just matching the trades themselves? Then we don't have to worry about know your own customer. So that was one of the cool things that we did. On that project, I built our GPU miner. So I had to learn how to program a GPU, and that was super cool. Like GPUs are actually really, really cool stuff, a really cool hardware. That's also where I learned to hate NVIDIA. And it's not for the reason you think. I don't really care about NVIDIA's marketing tactics stuff. Like, sure, NVIDIA's not great, and they kind of screw people over. But really what I hate about NVIDIA cards is they are prima donnas. Where an AMD graphics card, if you tell it to do something, it'll just do it. If you tell an NVIDIA card to do something, it'll look for any excuse to say, well, no, I'm not going to do that, honey. And NVIDIA cards are just so painful to work with, I can't stand them. After that, I worked on a binary serialization format because we quickly realized, hey, if we want to be churning through tons and tons of data really fast, we can't be using JSON. And we also wanted to account for every single byte, which is why we didn't use another off-the-shelf product for it that would have been, excuse me, that would have been smaller and faster than JSON. We wanted to do it ourselves because we want to be able to account for everything and make sure it works in the way that we like. So I designed that. Then I also designed a virtual machine that it's like what Bitcoin does with its custom transaction verification logic, where you have a stack machine that's kind of like forward. I built that for our crypto, and that was actually what we used to run our exchange. It was like it was just sort of super cool. But one thing I noticed is that programming this virtual machine is like actually really incredibly difficult if you're not in the mindset of reverse Polish notation stuff. And even then, the quote unquote opcodes we had for this virtual machine were like really awkward, so that we could like do things efficiently, but they didn't make sense to anyone who wasn't in our headspace about it. And so one thing I wanted to do was write a programming language that would compile to our to the quote unquote bytecode that our virtual machine ran. And I actually got a fair ways on that before we had to shut our doors because after the Bitcoin crash, we just couldn't get funding anymore. But that was like one of the coolest projects I ever worked on, and I did just tons of really cool stuff. After that shut down, at that point, like I had a crazy good resume because, like, oh, I've been working on I designed my own 3D printer in a 3D printing startup. I worked at a research and development lab. I worked at a cryptocurrency startup, and I was like a senior lead on that. And then it was just like a crazy good portfolio. And so I went to work for a company called RSI, which actually sort of turned to be like a big downgrade for me because I was used to doing all these super crazy awesome projects, and then our site was basically just a web dev house, and like I find web dev incurably boring. I can't stand it. But I did learn really get bitten by the programming language design bug in that time, so I've been studying that for ages at this point, which is actually relevant to what my project over here that I'm going to be talking about a little bit. It's a little bit part of the programming language design stuff. Um, But I worked for RSI for about a year, and that brings us to 2020 with the, well, you know what's going on right now, and that, like, finding employment can be kind of hard. I've been handing out my resume like crazy and haven't really got any bites yet. I'm not sure what's really going on, but whatever. What I have been doing, I haven't just been sitting on my laurels. I have another buddy. He's not really related to the cryptocurrency or 3D printing guys, or or with RSI, or with the R&D lab. He and I have been designing our own programming language because like we've been studying this stuff for ages at this point, and like we started following Jonathan Blow and his work on Giants. Like, holy crap, this stuff is so cool. We want to make our own. And like we think we can do a better job than all these other people. Also, because like we kind of hate most programming languages that exist. Like I have done a lot of work in Java, and I really hate that language. He's done a lot of work in C++, and he really hates that language. And we want better languages, and we want a language that like suits us, even if no one else uses it. And anyway, that sort of takes us to the present day in what I've been doing in the meanwhile. And you actually will see sort of a sample of the language we're designing. It doesn't really go into any of the cool stuff with language just because, well, I need to show you some of the stuff I'm doing with my named regions, regular expression stuff here. I need to show you like what it might look like, what syntax do I use. But I actually don't like pseudocode because pseudocode doesn't really tell you the implementation details of stuff as nicely as if you just use like a predefined language or whatever. Just when you see it, just sort of picture it like it's pseudocode if you don't understand what I'm doing with it. But anyway, so the second part of this video is the project I've been working on here, which is, I call it named regions regular expressions. Excuse me. This is a regular expression dialect, just like a PCRE, Perl compatible regular expressions is a regular expression dialect. This one is kind of a bottom of the barrel, dirt simple regular expression dialect, whereas PCRE has just all of these weird features, and it's like a super complicated programming language that actually winds up, maybe it's not Turing complete, but like it goes beyond what a regular expression dialect should be because it matches more than regular expressions. And it winds up being really complicated and kind of hard to use. I just wanted something simple that let me do most of the stuff that I care about doing with regular expressions without getting in my way. And so this is what I came up with. If you don't know what a regular expression is, just think of it as like specifying a pattern that text is going to, it's a pattern that you can use to analyze some text. And so for example, if I have a pattern here like this right here, Alice, and then the pipe operator, which is alternation regular expression dialects, or Bob. It's basically saying Alice or Bob. And so any text you give me, if it says Alice or it says Bob, then I'll say, yes, this matches a regular expression. So it's this kind of a, it's this kind of a text analysis tool. And regular languages are like, there's a whole Chomsky hierarchy where they're like regular languages, context-free languages, context-sensitive languages, recursively enumerable, and then a whole spectrum in between those. That's not really in the scope of this talk, although I'll have to talk about it a little bit. Just understand that regular languages are just very simple languages. They don't have any like nesting structures in them. They're just, you can sort of think of them as like a linear language a little bit. Anyway, down to brass tacks of what my thing is. Hold on, excuse me. I've been having bad allergies, just like on these two videos a lot, so I might actually snort a couple of times in this video, but whatever. So here you can see that I have this regular expression right here, and with this comment you can see that's actually equivalent to this regular expression. And so if you don't know how to read this, it's a /d is an escape character that means any digit, so 0 through 9. And then the plus character in this means, well, the last thing that you talked about, you need to have one or more of those. So this means the whole /d plus means one or more of any digit. Then R here is just a literal R. And then /w is sort of like /d, but for word characters. So anything that's alphanumeric and then an underscore. And then the plus thing works the same with that. And so if I were to just compile this, you would get into a state machine, because if you know computer science stuff and automata theory, you know that regular expressions are equivalent to state machines, which are, well, in terms of automata theory, a state machine is a finite automaton. In this case, we're working with a deterministic finite automaton. I'll get into that later, so you don't need to worry about that now. But anyway, this can compile to this state machine here. But you'll notice I have like this thing here that says region, colon, then start, radix, default, value, end. And where that comes from is, well, you have the start state of the state machines. Like, well, here's just where you start. And then you have the end state, which is like, if you reach this point, then like you absolutely did get a match, and your input text matches the pattern you specified. And default is like if you're not doing anything special with it, but the really interesting stuff here is radix and value. And these come from here and here in this regular expression, which is what I actually compiled to get this, although I compiled this by hand. So what this syntax does is I have an open curly brace, and then I have a name, and this is non-matchable. It's metadata that will basically be inserted into the state machine. And then I have a colon to say that, hey, I'm done talking about the name, go back to matchable characters. And so everything after the colon is a matchable character, and then I have the closing curly brace to end that named region. And you can actually nest this stuff, although I don't think I get into that in this presentation, but whatever. And so that's basically what happens. And the way that this is used is, if I go over to here, well, actually, I'll not get into that yet, but basically what will happen is, so I have my state machine, and I want to see if some input text matches the pattern of the state machine. So I'll put in the first character. So let's say the first character is 5 over here. So I'm at the start position, and if the input character is any digit, then I go to state 1. And so I go to state 1 over here. Excuse me. And what you see here is I have the region radix. And so when I go to that state, then I want my thing that like handles putting the character into the state machine to return the name of the region to me, so that like I have some way of observing what the state machine is doing. And then the next character is 0, and so if the next character is any digit, then go to 1 again. So you just keep doing that. So yeah, 5, 0, 0, 1. And then after that, you get to R, and then R will says go to 2, and the region here is default, so that's what it will return to me when I am doing my matching. It's like, hey, there's basically means there's nothing special going on here. It's just the default metadata here. And then with C, I do sort of the same thing with any digit, but here it's any word character. So we'll go to 3, then on 3 it'll do the winding around thing where it's like it can loop from go 3 to 3 to 3 to 3 to 3, so I can have as many of these word characters as I want. And when I do this, of course, it will return value instead. So I'll put in, so after R, I'll put in 2, that will return value, 3 will return value, 4 will return value. And then what will happen is if I get a null character, that's what this means right here, this /0, then it'll go to 4, and then the region will be end, or you could call it except or something like that. And that means, hey, you got a complete match. Everything worked. And so that's the like basic idea of like mechanically what this is doing. What this will look like in code is, okay, you can, this is the language, you can sort of see this as pseudocode, but basically, I have a multiple return here, so I have my state machine, I have an OK value, so like if something went wrong, I want to know about it, and if something did go wrong, I have an error value. And then I have this function here called compile regexp. I have my regular expression there, and I have some stuff to handle the memory here, because what we're dealing with is like a manual memory, what we're building is a language to deal with manual memory. And then I have the stuff for the handling the error stuff, so like if there was an error and this Boolean wasn't true, because like we have type inference, if this was false, then I want you to print out the error value, because this will be a string. Then I want you to panic, because like no reason to keep going when things are going wrong. And then here's the input, and this is sort of like the same thing as this here, just different value. And also, well, I'll get into this a little bit later, but if you know anything about Smalltalk, you can probably figure out like what I'm actually doing with this here and what this example actually means. But anyway, here's our input. It's 2R, and then whatever this binary literal is here. I'm just making some strings that like can grow, so something like a vector in C++, which shouldn't be called a vector, it should be called a growable array or something like that. Then some more memory management stuff, defer, which is defer-free, which is comparable to like RI and stack allocated things in C++, or if you RI where you have a heap allocated thing, and then at the end of the stack it just closes that thing if you're not doing like automatic reference counting stuff. That's basically how you can look at defer if you're not used to thinking about it from a language like Go. And then over here we have the index, and if you look over here, the start state is always index 0. And so this way, if you're starting a fresh match, you can just like go to 0 and just keep going. And I have a for loop, and we have variable shadowing, so this here doesn't actually conflict with this, so it doesn't matter. I have a for loop where I have index here, so I can keep track of what the index is as I'm pumping the characters into the state machine. I can get the region out, and I can get an OK, because like if I don't actually get a good match, like if I go back to here and on state 1, I input the letter A, well, that's not a digit, and so like this doesn't actually match. And so OK here will tell me if it matched or not. And then I can like say the match failed and then panic or whatever. Anyway, the pump regular expression function, what that does is it takes a character, the current index, and the state machine, and does whatever stuff it needs to do to see if the character can transition anyway on the state machine, which if I haven't already said this, the state machine is like a flowchart. And then it will return to me like, well, did it work? What was the region name that we moved to? And then what's the new index? And then that just gets stored up here, and then I can just keep looping over it. But what I can do here is if the region is radix, then I'm just going to start appending the characters to the radix string. If the region is value, I'm going to start appending the value, the characters to the value string. And so this way I can strip out this value and this value and store them in their own strings. Or for this one, I can strip out 5,000 and know that belongs to the radix, and 234 know that belongs to the value. And then if I take this to the end and I can print this out, this string right here should print something like radix colon equals 2, and then value colon space, and then whatever that binary literal is. And that is just like a pretty simple example of how to use this stuff. You can say there's a lot of boilerplate here, and I do get into that in just a second, but I do want to talk about like a use case for why you would want to use this is if you're designing a programming language and you want to be able to have numeric literals have arbitrary base, like instead of like doing what is it 0b for binary or 0x or whatever for hex. If you just want to be able to type in exactly what the base is and then keep going, well, that's sort of what you can do. This is sort of like how Smalltalk does it, where I specified the base of the numeric literal. So this is base 5001, and then I have my little delimiter here so that I know when I'm talking about the base and then when I'm talking about the value. And I have the value, and this is like some crazy huge number, base 5001. If this were base 10 here, then this would be 234. And so this is like a very quick and dirty example of like something that you might care about if you're writing a compiler, where this could really help you. Anyway, so all the stuff I wrote back here, it's actually a lot of boilerplate, but you don't need to dig into that boilerplate if you're not actually doing some very particular matching stuff, because the most common matching stuff, like say I have some string, I want to see if it matches this state machine. Well, I can provide a matching function to just do that for you. So here I'm compiling my state machine because like the state machine should probably be a long-lived object because like it can just be reused over and over and over again. You just have to use a different index variable and set it equal to 0 to just restart using it. But so I have this, and so well, I guess if in that case you might not want to defer it, just like it stays around. As long as you have a handle to it, it's fine. It's not memory leak. But then I can have this function here called match regexp, where I have my string that I want to match to the regexp, then I have the state machine, and then that will return true or false. And like that's super easy to do. That's nothing. And if you need a more sophisticated matching behavior, you have access to the state machine. You can do stuff like this, and it's really cool, really nifty. You can do lots of stuff. So, for example, one thing you could do is you don't have to just match text. You could also, like if you're writing a parser, you could also match tokens, and it wouldn't take much to modify this to work with tokens. You could match button presses from the user. You can match story flags in the game. You could do lots of cool stuff like that. And one of the really nice things about this is because it's not like a PCRE where it has to match all at once or not at all. I can just be matching this slowly over time. Like if I need to start matching something and maybe I want to respond to like how that thing is matching, but I don't have all the data yet, I can just be slowly churning on this as I'm going through doing other stuff and more data gets available to me. And I can do lots of really interesting stuff with this. I don't know how much of this is useful, but I'm certainly interested in trying it. Excuse me. And really the thing about this is I want to be able to talk about state machines in a language that's designed for talking about state machines, which is basically what regular expressions are. And so the other way to like talk about state machines in programming is to use like switch statements, just switch statements on switch statements on switch statements, and those get really complicated and convoluted and like hard to handle really fast. They're certainly doable and they're more reliable than just having a lot of like free state around, which could cause like crazy bugs. And so like I do see this as an alternative to switch statements sometimes, not always, but sometimes, because I'd rather write something like this to be able to specify what the state machine actually needs to be doing and then react to that in a very simple way than have to like write out something larger. Although this case is actually pretty simple, but if I had something a lot more complex, like I'll show you in a minute, like maybe it would start getting a lot easier to just type in regex in a regular expression than type out a whole state machine in switch statements. Though I don't think it would always be a replacement, but whatever, I've stayed on this point too long. So something I've done with it. I have this regular expression here, which the way to read this is, so here's a region named person, and it's one or more word characters, then space, then the word is, and space, and then here's another region, and it's called article, and the values that can go into article are a, an, or the. If you don't know what the question mark quantifier does, it's sort of like the plus quantifier where it means the plus quantifier means one or more of what just happened. This means 0 or 1 of what just happened. And so that's how you get a or and there. And then you have space, and then you have the last one, the last region, which is called adjective, which is any character that is not a period, and one or more of that. And at the end you get a period. And so what happens here is when you insert a value or some text into this, if it matches, like say Alice is a good accountant, what it's going to do is it's going to strip out Alice, it's going to strip out A, it's going to strip out good accountant. And then over on this template, it's just going to paste those in. And so when I give this thing Alice is a good accountant, it's going to do I agree. Alice from the person region is A from the article region, and then good accountant from the adjective region. And the reason I was doing this is because I was working on a Discord bot where I thought it'd be really cool if like people could type stuff out and they could do some more sophisticated text analysis to do some interesting replies to people. And like this is just a toy use case of this thing, but it was actually really fun and a lot easier to work with than I thought it would be because of some stuff I'll get into later. But it just ended up being really nice. And so like here's some other examples of like how this specific thing would work is Alice is a good accountant turns into I agree. Alice really is a good accountant. Bob is the coolest guy I know turns into I agree. Bob really is the coolest guy I know. Or Carl is an idiot, and then it says I agree. Carl really is an idiot. And so here we get to the caveat. And this is for the two versions of this I've written so far. One I wrote in Odin, which is almost a really cool language. I almost really like the language, but the problem with the language Odin is It's not really mature yet. I ran into a lot of compiler bugs, and so it's hard to do really sophisticated stuff in it. When that language gets mature, it will absolutely be worth using, but by the time it gets mature, I'm hoping to be using my own language. So this is a tentative endorsement of the language because it is about the bare minimum of what I consider a good language should be, but it's not quite there yet. It's almost there. It will be a good language. I believe in the project. It just needs to iron out a bunch of compiler bugs. And the other one I've written is in Java, and the reason I did that is for the I was using there's some library for doing Discord bots through Java rather than JavaScript. I was like, okay, well, I'm just going to write this thing in this Discord bot in Java rather than in JavaScript because I don't want to touch JavaScript. I'm not that much of a masochist. Which is hilarious because I was touching Java, which you have to be something of a masochist to enjoy Java. Anyway, let's see. Okay, so in both of these versions of it that I've written, it has this problem where if you have a regex like a regexp like Rob or Robert, this actually has to be a compile error because when you build the state machine for this thing, you don't have to worry about most of it, such as where this after completeness. But if you look at the start state and the transitions from it, if the input characters are, go to 1, or if the input characters are, go to 4. Well, which one do you go to? You can't know. And so if you're doing something like this, where you're just going through it entirely linearly, which is what I actually want to do because like that's really fast, you actually can't do that because what happens is you have a non-deterministic finite automaton here, where what you need for my stuff to work is you need a deterministic finite automaton. And there are lots of technical reasons for why this is important, but the basic idea is to match with a non-deterministic finite automaton, or an NFA. I'm just going to say NFA and DFA, DFA for deterministic finite automaton. With an NFA, to match that thing, you have to be able to do some backtracking stuff, and you can't ever really be sure that you're on the right path for it. You have to do a lot of work to make sure that like you're actually doing the right thing, and you have to do all the matching at once. So all the cool stuff you can do with my thing, you just can't do with an NFA. It just doesn't work. And so this right here has to be a compile error with my stuff. Except it doesn't exactly have to be, because there are algorithms that will convert a non-deterministic finite automaton. Well, I said I was going to use NFA. Will convert an NFA to a DFA. This can cause like a huge memory explosion, but like it can be done. Except it can't be done perfectly, because if you look at this example right here, where the Rob and Robert are in 2 different regions. Well, if you look at this state machine right here, if you go to 1, well, the region is default, and if you go to 4, the region is default. It's clear what region you're in, and so you can just go ahead and do this. It's not a problem. You can go ahead and like repair the NFA and turn it into a DFA, and you're not going to have an ambiguity problem about which region you're in. But if there is going to be an ambiguity problem, like with this regular expression down here, you can't really do that because it can't return the exact right region to you. It can't know what region it's in. And if it starts doing some stuff where like it returns, well, both regions, why doesn't it just do that? Well, but what if you run into this issue again, and you have both of these branches? Well, it has to return has to return A and then C and D, and then B and C and D, and it's just like you get into like a huge exponential explosion of state that you really kind of want to avoid if you're trying to do software fast, which is what I'm trying to do with this. And so there are just some states where it just has to be a compile error. And I will eventually probably like solve this and like make it work. I think I'll have a flag for like if you want this setting or not, if you want it to do the NFA to DFA conversion or not. Because NFA to DFA conversion is just like a huge explosion of state, and the direct method from DFA from a regular expression to DFA that I use can already make quite a bit of state. Like these are pretty memory hungry things. Like luckily we live in an age when memory is pretty free, but whatever. You don't want to have like a gigabyte dedicated to just a regular expression. That's ridiculous. You don't want to be doing that. And so I think I'll have a flag for that, just so that people can say, oh, well. Also note right here, Rob or Robert can be written as Rob and then option and then ERT question mark here. That's the other reason why I think it would be nice to not have to worry about this stuff so much with the NFA to DFA conversion, because you can just like rewrite things to work in a decent way anyway. And in my experience, that works reasonably well. But I do see that some people are just going to want it to just work without having to worry about this weird problem, which I do actually have. You can actually check for this. That's actually really easy to do. Well, it can be really easy to do. Unicode turns that into kind of a nightmare. If you're just dealing with ASCII, it's easy to do, so whatever. And I'm sure there's a way to do it with Unicode. I just haven't thought about it enough. But anyway, I've probably been hammering on this point a bit too long, but the basic idea is this can be solved. I haven't solved it yet. It's actually pretty easy to solve because the algorithms aren't that complicated for doing this. It's just there's some considerations where maybe you don't want to solve this because once you get into the mindset of how to use this, it's actually pretty easy to get around the problem. And the cases where you can't get around the problem, you couldn't get around it anyway, adds a lot of complexity to the thing and also adds a lot of memory usage. Maybe there's a good argument for not doing this and just seeing how well that works. And then potentially having a flag on the side for someone who just wants it to work and they're willing to eat that cost. But anyway, that's sort of the caveat. So I mentioned that I have an algorithm for turning a regular expression directly into a DFA, or in this case, an NFA. Excuse me. I have an algorithm for doing this. This is actually one of the weirder things about this project, which is when I was looking up how regular expressions work. Excuse me. That it's actually really hard to find information about how regular expressions work. Because if you Google, well, how do regular expressions work, you find lots of articles explaining how to use regular expressions, which isn't really what I wanted. And once you get past that and you start figuring out what to search for to be able to find more stuff about this, you start learning more stuff about how to generate NFAs from a regular expression, which is not what I want, because I want DFAs, because DFAs let you do things in a linear fashion. They have all these really nice properties that maybe sometimes you want to take advantage of, and finding out the exact algorithm for how to do this was actually really kind of a chore. And part of the problem I have with this is I have no idea what this algorithm is called. The best name I've ever heard for it is called the direct method. But if I Google that or look for Wikipedia, like, I get very inconsistent results. I don't know that's actually what it's called. And I don't know who came up with it or what research there is out there for it. It's just really hard to find information on this algorithm. And it's so weird. And I've read around that apparently you can find a description of this algorithm in the Dragon book, which is like it's a book for like teaching you how to build compilers and stuff. And I've looked up several editions of the Dragon book and tried to find where this algorithm is described in them, and I just can't find it. And so I've just been looking around for, when I was doing the research for this project, I just had to look around for just drags of the internet to find what I needed. And some of the stuff is easy to find. So, like, I have this table up right here, and this is really important because this table is like one of the rarest things on the internet. Because with this table, you can find everything from this point here up, so the clean star up to the epsilon node. You can find that stuff relatively easily. But the stuff with the plus operator and the question mark operator, it is almost impossible to find a chart that will tell you how to implement those in the direct method. And part of the reason for that is because you kind of don't need those to implement them, because you can compose those operators out of like epsilon nodes and clean stars and the concatenations and alternations. You can compose this behavior if you really want to, but the problem is when you're trying to compile a regular expression into a state machine, you really don't want to have to be dealing with those kinds of weird compositions. Like, if I had to do the thing where it's like, well, there's a plus here, that means I need to, like, do some manipulations to the parse tree on this to this thing to actually, like, do the behavior I want. That is actually really... It's not hard to do, but it's really memory intensive. And the reason why it's memory intensive is because it makes it harder for you to make good assumptions about how the compiler is going to behave. And that can cause sort of a memory explosion depending on what you're doing. And it's not good to be doing things that way. Like, being able to have these two parts of the chart to explain more about how to implement things efficiently just really helps when you're implementing a direct method regular expression to DFA compiler. It's just, I almost consider a necessity, not quite, but almost. And so that's why I'm showing this chart here, just so that there's some other record of this chart out there, because it took me forever to find this chart. And the chart was actually wrong when I found the chart, because I think it was this slot right here on the plus node under nullable of n. It said true here. No, it's not true. It's a nullable of C1. And I had to modify that, and that made me like really annoyed, because like, well, is the rest of this even correct then? So I had to actually implement this to see that was correct. And so if any of you are interested in learning the direct method for compiling a regular expression to a DFA, this chart right here is what you absolutely need. This is pure internet gold as far as I'm concerned. But anyway, enough about this. Now to the last part of this presentation, which is why. Why should something like the named region's regular expression dialect exist? Like, what's useful about this? And so, the big problem that you run into with NFA regex engines is they suffer from a problem called catastrophic backtracking. And here it says like the state machine produced by Robert is an example of an NFA. I have this link right here. I'll put this in the video description. If I forget about it, go ahead and yell at me. But it talks about like what catastrophic backtracking is and how awful it is. But I've got an example from the website here. I may not be exactly right, but showing just what's bad about it. And so what happens with catastrophic backtracking is, so I talked about with this here that if you were going to try to match with an NFA, you would have to do some backtracking stuff. So what this means is, okay, so my input text is Robert, and I want to match it against a state machine. So in order to do this, it has to go to R first. It has to like just start matching and hoping it works. So go to 1, and then it'll see O, go to 2, it'll see B, go to 3, and then what it won't see is the null character, here, which is the sort of the accept state thing for this. You won't see that. Instead, it'll say E, and so it's like, oh, hey, something's wrong. I need to backtrack, and it'll backtrack until it gets to here, and they'll start going forward, then it'll be able to match correctly. And so it needs to be able to do this sort of back and forth backtracking stuff to match when it can't be sure that's on the right path for matching. And that is incredibly expensive. Well, okay, it can be fast, but in really bad cases, it can be expensive. And what will always happen is, in order to prove that you don't have a match if your input doesn't match, is it has to basically go through every single iteration to show that no match is possible. And that's what gets really expensive. Not matching is what's expensive when you're dealing with an NFA regular expression engine. And so here are 2 examples. So with this regular expression, in parentheses x plus, and then plus at the end and y. With this input here, if it starts trying to match this, it'll grab all of the x's, and that will match this correctly, but it won't match this, and so it'll fail. And so I'll have to backtrack, and then start matching all of these, and then leave 1 left over for this, and then that will succeed, because then it just goes to the y and it works. Now this is already more expensive than what my DFA thing would do, because my DFA thing, well, okay, so we have a caveat here. This thing here does run into the sort of Robert problem here, where it turns into an NFA. But if you had that thing solved with the NFA to DFA thing, this would just work. You would just go x, 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 and then there's a y, and then a null termination character, and then it works. And it would just like do it linearly and super fast. And so you can see that this is potentially already slower. Now there are some reasons why it might be faster that have to do with the cache and like whatever. I'm not really interested in that. Just you can see that this could be slow. Now the example where it's really slow is this one right here, where it's not actually a match for the regular expression up here. Because like, well, this fails for the same reason that this failed. Then you put this here, but then the y fails. But it hasn't proven that there's no match yet, because this regular expression can be arbitrarily complicated. And so it has to start doing all of these different permutations on and on and on and on. And I may not have written this out correctly, but basically it can take tons and tons of time to go through every iteration to show that no match was found. And it's just an insane amount of work to prove that no match has been found, when with my thing, it's, let me find state machine here. If I go to any of these states and I insert a character that here is not a digit or it's not R, no match is found. You know immediately. And the worst case scenario for my DFA thing, or well, for DFAs in general, is if you match, that is your worst case scenario, and your time complexity there is big O of n, where n is the size of your input. And so that's like a really nice feature to be able to have. It's not that it'll always be faster than NFA, because again, there are cache issues here, or CPU cache issues, but it does mean you're never going to run into an exponential explosion of the amount of time it'll take. It's very bounded, it's very stable. Let's see, alright, so yeah, that's just what I got over here. And so what sort of turns out about this is, okay, so normal DFA regex engines, they sort of lack the power of modern NFA regex engines, but they don't have to, because, well, what's nice about my engine over here is I can start naming regions, and so here I have like some data as code kind of thing, like maybe you can think of it as like a homoiconicity thing like from Lisp, but I have some data that compiles down in, some code that compiles down into some useful data. And then I have these names that are in that data that I can use to store hooks, so that my normal code in the language I actually want to be writing everything in, because like writing really complicated PCRE regular expressions is like just a nightmare. It's utter cancer. I would much rather be able to write something simple with this and then put in these hooks and then have all the complexity live in the language that's actually designed to handle the complexity very well, which is basically any general purpose computing language is more or less going to be able to handle the complexity better than PCRE will be able to. And so like that's one of the big things about this is I want to be able to do regular expression matching, or well, anything to do with state machines, and I want to be able to do it in a powerful way, but without putting too much responsibility on the regular expression language. And the next thing is modern NFA regex engines like PCRE. They have a lot more in common with context-free language identifiers or parsers than they have in common with regular language identifiers, because PCRE can identify way more than just a regular language. And if you don't know what that means, I think I mentioned it earlier in this video, but that might have been a different take, whatever. Basically, a regular language is a very simple language. A context-free language is a bit more complicated language. And a regular expression is capable, regular expressions are capable of matching regular languages, but not anything more. PCRE and stuff like that, they're capable of matching more than just regular expressions, because of how complex they are, and because they take advantage of some maybe kind of nice properties of NFAs. But really, what's happening is with like PCRE, and so you've got a context-free language identifier, maybe something erring on context-sensitive, depending on some of the features in PCRE. I haven't studied that too much. But the thing is, if you're going to be doing context-free identification, like with a context-free parser or something like that, well, just using something like a PEG parser is a lot nicer than using PCRE, where PEG here stands for parsing expression grammar. And so what I would kind of like to see is a world where if you need to do regular expression matching, you can have fast and feature-rich regular language matching with something like my named region's regular expression dialect. But then if you need something more sophisticated than that, that starts getting into needing to do with catastrophic backtracking issues because you're dealing with NFAs, then just be honest about what you're doing and start using something that's actually that can actually handle context-free languages without having to be a weird hack on the idea of something that is not meant to handle that kind of stuff, which is kind of what PCRE is. It's something that's been grown kind of organically from very humble roots to like include all these crazy features that just don't need to be there if you actually have a tool that's right for the job, which is what something like a PEG parser is going to be. And then I guess the last point about this is I think PCRE can do some context-sensitive matching stuff, and that's really cool. And just on their own, my named region's regular expression dialect and a PEG parser can't do that stuff. But you're not without hope, because if you need to get into something that complicated and that needs that fine of a touch, well, with both of those things, you can kind of get into doing stuff like this, where any of the complex behavior you can handle in a language that is really meant for dealing with the complex behavior. And so there are things with various parsers where, okay, well, if you parse into this state, then start running this user code. Like, you can do stuff like that. In fact, Even PCRE can do that stuff, I think. But anyway, like, you can start getting into doing that stuff. I prefer way more like my named regions regular expression dialect does it, where you don't have to, like, include the code into the regular expression to do it somehow, like with some name reference or something like that, because that's, like, way too complicated. But just have it where, like, okay, I've got a thing that's nice and useful to use, and I can just start working with that. Like, I think this is a nice way to do it because you're not really hiding anything behind weird layers of abstraction, just needing everything really nice up front so people can use it. If they need to do something special, they can go and do something special. And that's why I think this is actually a, if not a good idea, at least an interesting idea that's worth exploring. And anyway, that's about it for this project and also the stuff I've been doing. I hope you've enjoyed this video. It's about 45 minutes long at this point, so hopefully I haven't rambled on too long about stuff that no one but me understands. Because like that's a weird thing that can happen with projects is you get so invested into everything and you think it's so simple that you can go to explain to people and like, what is this alien language that you're talking about? And it's like, what do you mean? It's so simple. And so hopefully I haven't done that, but this is what I've been. This is the kind of stuff I've been doing for the past couple of years, and where I've been, and just where my life has led me. And so, I I don't know that I'll get back into making videos regularly. If I do, it'll probably be content more like this. And I just don't know what the future of my channel is going to be, but I at least wanted to touch base with you guys, let you know that I'm not dead, I'm doing alright, I'm doing some interesting stuff. I do have Studio Series Devastator, that guy is huge, and there are some things on him, like, people say that, like, his little hat thing doesn't actually clip on. It actually does clip on, actually, it clips on fairly well. I may review that guy, I don't know, but, like, I am still collecting, not as much as I have, but anyway, this has been me, and I hope you've enjoyed watching this. I will hopefully see you guys later. Bye.